Hi, I'm Max Hopkins. I'll be talking about the spectral and combinatorial structure of walks on expanding posets. And this is based on joint work with Jason Gaitonde, Tali Kaufman, Shahar Levitt, and Ruji Zhang. Okay, I want to start off with some motivation before sort of diving into this more technical material about expanders, high-dimensional expansion, and generalization to posets, and in general, why maybe you should care. Okay, so to start off, what are expander graphs? I'm sure many of you know, but just so everyone's on the same page, these are basically, expansion is sort of a robust notion of connectivity, usually in sort of considered in sparse graphs. You can think of it as sort of a way to generalize or mimic the type of structures seen in the complete graph. It's defined on graphs in sort of many morally equivalent ways. You'll hear of things called spectral expansion or more combinatorial or boundary type expansions like edge expansion and vertex expansion. We'll consider a couple of these in this talk. And expanders have sort of now long been a ubiquitous tool throughout theoretical computer science, through areas like complexity, algorithms, coding theory, really sort of most sub areas you can find, usually some very important use of expander graphs. So these are very important objects. And recently, there's been a lot of interest in sort of extending the success of expanders to higher dimensions. It's something called high-dimensional expanders. And this has indeed been very successful in the past 5 years or so. It's led to a number of breakthroughs in approximate sampling, very recently in coding theory, in agreement testing, implicitly in some older results as well that we'll talk about. And most, but sort of not all of the above, I'll mention some special exceptions. Most of these works on high-dimensional expansion study a generalization of graphs to higher dimensions called simplicial complexes. Basically, these are just downward closed uniform hypergraphs. So in other words, here we have sort of a 3 uniform hypergraph, x3 at the top level, and then we downward close it to get the associated simplicial complex. And when do we call a complex a high-dimensional expander? Well, we'll take sort of a recently popular local definition that more or less says that a complex is a high-dimensional expander if every sort of local component or every restriction along the complex is an expander graph, in particular a spectral expander. So briefly, sort of what does this mean in a little bit more detail? Well, looking at sort of a restriction or what's called a link, you look at basically a face and you look at everything that contains that face in the complex. So here is 1, here's everything that contains 1. To get the link, you would now remove 1, which would give you a graph, right? Basically where, these edges now become vertices, 2, 3, and 4. And these triangles become edges, 2, 3, 2, 4, and 3, 4. And this is a graph where you can talk about its standard expansion. So if sort of all of these local graphs are standard expanders, it means that this underlying high-dimensional complex is what's called a high-dimensional expander. Okay, great. So much of the success of expander graphs comes from sort of their classical association with the random walk underlying the graph in question. This is just the walk that sort of, walk on vertices of the graph that starts at a vertex and moves to a uniformly random neighbor of that vertex through an associated edge, right? Nothing complicated. A lot of the success of high-dimensional expansion, especially in sort of approximate sampling and agreement testing, is largely driven by sort of natural analogs of these walks on complexes. Natural high-dimensional analogs, first introduced by Kaufman and Mass. And the basic idea is that on this standard walk, you sort of move between vertices by a connected edge, right? You might move from the vertex 1 to edge 1, 4, back down to vertex 4. That would be sort of a standard step in the basic walk on graphs. And the observation is that you can do this at any level of a simplicial complex, right? We could basically move between 2 edges by a triangle that contains them, right? So we could move from 1, 4 to 1, 3, 4 to 3, 4. And this would give some higher order analog of the random walk underlying a graph. These are called higher order random walks. And the reason essentially that this has led to so much success is that it turns out that these higher order random walks on simplicial complexes, on high-dimensional expanders in particular, recover a lot of important structure that was already important in the literature. Sort of basically, in the most basic case of the complete complex above, these give what are called the Johnson graphs, which are already important objects. You can embed, the hypercube in such a way that this walk gives you exactly the hypercube graph or the noisy hypercube graph. On Ising models, this gives you what are called or a variant gives you what are called the Glauber dynamics, which were extremely important for all these breakthroughs in approximate sampling. Okay, I won't belabor the points, but the idea is that this captures sort of a lot of important structure throughout a lot of areas of TCS, turns out. But on the other hand, sort of simplicial complexes are not the only generalization of graphs to higher dimensions that you might want to consider. And it actually turns out that several of the sort of recent major breakthroughs based on this type of material rely on generalizations very particularly to non-simplicial structure. So I'll give sort of two main examples of this. The first is the proof of the 2-to-2 games conjecture, which relies basically on a walk on what's called the Grossman poset. It's basically the Q analog of simplicial complexes that we looked at before, where sets are replaced with vector spaces. And it's very important that you have sort of this linear structure in your underlying complex that doesn't show up in the simplicial case. The second case, which we'll focus on a little bit less, is these recent resolutions of the quantum low density parity check codes and the NLTS conjecture, which were these big problems in quantum complexity. And these were solved recently using sort of notions of high dimensional expansion on cubical complexes, which I won't go into too much detail, but are in some very crucial way non-simplicial. It turned out very important to sort of move away from simplicial structure to prove these conjectures. Okay, so that said, there sort of is a way to generalize all of these objects into one framework, which is the framework of ranked posets, or graded partially ordered sets. And in fact, we basically already seen this. When I drew out this diagram of the simplicial complex before, I was already drawing it in what is essentially poset form, as a partially ordered, a ranked partially ordered set, where the ranks are given by the size of the set, right? Here's rank 3, rank 2, rank 1, and rank 0, and things are ordered by inclusion, right? This is an example of a partially ordered set, but these elements don't have to be subsets of 1 through n, right? They can just be sort of generic elements. Maybe they're vector spaces, maybe they're like squares and edges or something like that. They don't have to stand for sets. That's just what it looks like in the simplicial case. And they don't have to be downward closed. They don't have to satisfy sort of these types of simplicial structure. You can look just sort of more generally at any type of ranked poset structure, and that captures a broader set of problems. Okay, it's not particularly hard to generalize sort of the local notion of high dimensional expansion to posets. Sort of generalizations of high dimensional expansion to these objects were first considered by Dixie, Filmus, and Harsha, later in this local notion by Kaufman and Tesler more recently. The way you extend this definition, I'll be now a little bit more formal with how we define high dimensional expansion, but it's basically the same thing. You're just going to look at all of the local components of this poset, sort of local graphs on this poset, and you're going to require that they're good expanders. So in particular, we'll look at all of the links. So here we're looking at the link of 1, and we'll look at this sort of up-down walk. Basically, this bipartite thing here gives you a bipartite form of a graph. You take the up-down walk on it. This gives you some sort of underlying weighted graph or random walk, and we can talk about its expansion. And so basically, we call this complex an expanding poset if every restriction, if every sort of link, the up-down walk is a good spectral expander. So in other words, sort of for all restrictions of the complex, if you look at the largest non-trivial eigenvalue of these walks, of these local walks, we want that to be at most gamma. And okay, if you haven't seen spectral expansion before, this is a little bit of a confusing condition, but it sort of says in some way that it acts like the complete complex. You can just think about it like this for simplicity. Okay, so now I can sort of state the main motivating question of this work, now that we've gone through this background, which is how does underlying poset architecture, sort of the underlying structure of the poset, how does this affect sort of structure in higher order random walks? And in particular, how does this affect the spectrum and combinatorial structure of these walks? And the reason that we care about this is to sort of understand, given a certain problem at hand, what sort of underlying poset architecture should we try to use? At the moment, we sort of know that different poset architectures are important for different problems. By the examples I gave before, right? In approximate sampling, we really needed this simplicial structure. In quantum, we needed these cubical structures. In hardness of approximation, we needed this linear structure. where are these coming from? Sort of what are the main differences between these architectures? So we'll focus on sort of one concrete motivation throughout this talk, which is work towards the unique games conjecture, Coates' unique games conjecture, which is, I think, widely agreed to be the most important open problem in hardness of approximation. I won't talk too much about it. What I'll say is that the sort of recent breakthrough you can kind of think of halfway to the unique games conjecture, the proof of what's called the 2-to-2 games conjecture, basically relied on characterizing exactly these properties, these spectral and combinatorial properties, on what's called the Grossman-Poset, which is basically just the simplicial complex we looked at before, but everything is replaced with vector spaces. So a set of size 3 would be a vector space of dimension 3, and so on. And basically the properties that mattered were sort of understanding decay of the spectrum of sort of a natural walk on this poset that end up giving you what are called the Grossman graphs, and understanding sort of their combinatorial structure, something called non-expanding sets that I'll talk about a little bit later in the talk. And there's sort of a reasonable hope there was an approach proposed towards getting further towards the unique games conjecture by Barak, Kotari, and Streuer, which basically said, if we could maybe have some more general understanding of this type of result, maybe on higher degree variants of the Grossman or more general objects or sparsifications of these objects, that there might be some way past 2-to-2 towards the unique games conjecture. So there's some concrete motivation of understanding sort of similar or how these things change with different poset architectures towards proving the UGC. I won't go into much more detail than that, but that's sort of the concrete motivation for understanding this type of structure and posets. Okay, so with that out of the way, let's get into a little bit more detail. First, I want to talk about characterizing the spectral behavior of walks on expanding posets, high-dimensional expanders. Okay, so first of all, to sort of make our results more interpretable, we're going to make the assumption that our posets are regular in some fashion that's satisfied by sort of most standard types of posets considered in the literature. The first assumption we'll make is that these posets are downward regular, which basically means that any given rank k element will be greater than the same fixed number of rank I elements. So on a simplicial complex, what does this mean? Every k set is bigger than exactly k choose I sets, right? There are k choose I sets contained in every k set. That's sort of all this means. But more generally, instead of k choose I, we can have some regularity parameter rki. And the second is sort of a little bit more technical of a regularity condition, something called middle regularity. And it basically promises that the sort of order structure in your poset is like nicely spread out, is sort of uniform in some manner. Formally, it says that between sort of any rank I and rank j elements, there are the same number of paths, like ordered paths between them. Again, this is something satisfied by most classical examples like simplicial complexes or sort of the Grossman poset. And it's more of a technical condition we need for sort of averaging and various technical tools to work out. Okay, so the first thing that we prove is that higher order random walks on regular expanding posets exhibit something called spectral stripping structure. And in particular, we give the following characterization of the spectrum of higher order random walks. So if X is a, say, k+1 dimensional regular gamma E poset, then this up one, down one walk that we talked about before on rank K elements has basically exactly the following spectrum. It lies in k+1 strips, where each strip has sort of, all of the eigenvalues are highly concentrated in these strips of width sort of O of gamma, where gamma is this sort of strength parameter, a quantitative expansion of the underlying poset. And moreover, somehow these eigenstrips correspond combinatorially. The ith strip corresponds to functions that sort of come from rank I in some sets. So that basically these are functions that are maybe like lifted from the ith rank of the complex up to level k. The details don't matter quite so much, but somehow these are functions that come from level I. And moreover, sort of the approximate eigenvalues within each of these strips is exactly characterized by the regularity of the complex. And I'll say something about this in a little bit more detail in just a second. So I guess broadly, this is a little bit hard to interpret. What is exactly this sort of RKI over RKI plus 1 means? Well, sort of an important consequence of this theorem is exactly that the regularity of the poset dictates how the spectrum of random walks decay across levels of the complex, across ranks of the complex. This is basically an analog of sort of what's typically called threshold rank on graphs, sort of how many large eigenvalues are there. Now it's like how many large strips of eigenvalues are there. This is called stripped threshold rank. It was introduced in some earlier work with Bafna. And this is not only a crucial parameter, it turns out, in the proof of the 2-to-2 games conjecture. I'll talk about this a little bit more concretely in a minute. It was also shown to control sort of runtime for various sum of squares algorithms for unique games on high-dimensional expanders. This is a very important parameter. It controls sort of spectral algorithm and spectral behavior on these objects, on these walks. And okay, a little bit more concretely, what does this look like on some basic examples? Well, for simplicial complexes, we already said that this regularity parameter, RKI, is k choose I, and you can, what is sort of k choose I over k choose I plus 1? You can compute that the spectral decay looks about like 1 minus I over k. So you look at the I strip, you get eigenvalue about 1 minus I over k. So this is basically linear decay from, across levels of the complex, right? And maybe sort of the relevant thing to notice is that if you want to get to some constant eigenvalue, you have to walk linearly many levels in the complex. You have to go very far, very many eigenspaces in to find something with a small eigenvalue, with a constant eigenvalue. Now compare this to what's called a Q-simplicial complex, which is basically the vector space analog. These are like subsets of the Grossman poset. And here the regularity is much, much higher. The regularity is k choose I q, the q binomial coefficient. And I won't write out exactly what this is, but going through the same calculation, you get that the ith eigenstrip is about q to the negative I. So quite small, right? Even going to the second eigenvalue, if q is 2, you get about a half. Right, so now to get to some small constant eigenvalue, you only have to walk constantly many levels into the poset, and this, it turns out, is a big difference. It's sort of it crucially underlies why you can get, for instance, a 2-to-2 test in this application to hardness of 2-to-2 games. It also allows for sort of faster algorithms in the HDX case, because sort of there are fewer eigenspaces that have sort of the relevant structure you have to look through. So this decay of eigenvalues is quite important, and the major takeaway here is that basically stronger regularity of your underlying poset implies stronger spectral decay, that you sort of have nicer spectral behavior in some sense, the more like strongly regular your poset is. Okay, I want to briefly talk about the proof of this, since we give some sort of nice improvement over the methods in prior work. So the idea is sort of based on these ideas from previous work on simplicial high-dimensional expanders with Bafna, where basically we look at an approximate eigen decomposition for high-dimensional expanders and show that this implies the spectral stripping theorem. And we give an improvement of that in this work. We basically give a tight version that shows if you have what we call a delta approximate eigen decomposition of some walk, which basically just means you have a decomposition where every function in the decomposition is in L2 norm close to being an eigenvector, right? There exists some approximate eigenvalue lambda I such that mfi minus lambda I fi is small in L2 norm, so it's like almost an eigenvector. Then any self-adjoint walk that has such an eigendecomposition, that has a delta approximate eigendecomposition, basically has to be divided into these spectral strips for each space in the decomposition. So basically the spectrum of M has to be very, very concentrated around these approximate eigenvalues lambda I. In particular, if you are have this delta approximate parameter, you're actually within plus or minus delta exactly. And this is tight. You can see this by taking like maybe a true eigendecomposition and like shifting it by delta. This is like exactly what you'll get. So this is a tight version of this theorem that basically says if you have an approximate eigendecomposition, it tells you something very strong about what the spectrum of this walk looks like. I'll very quickly sketch the proof, since there was a sort of very complicated linear algebraic way we proved this previously. But now there's a much, much simpler method that's really only a few lines. The idea is just for every space vi, for every I, to consider the operator m minus lambda I times the identity squared. And the idea is that by Courant-Fisher, by the variational characterization of eigenvalues, this approximate eigenvalue promise here, it exactly tells you that Mi has dimension Vi eigenvalues less than delta squared. And right, when m minus lambda I squared has eigenvalues less than delta squared, this implies that m has eigenvalues within the range lambda I plus or minus delta, right? Because we're subtracting off lambda I times the identity. So this just sort of shifts the eigenvalues. But we have a true decomposition, right? The sum of these dim Vi is equal to dim V, which is the total number of eigenvalues. And so these must account for all of the eigenvalues in your space. And that's the full proof, right? It says that every sort of separate subspace has all of its eigenvalues within this small strip, and that accounts for all of the eigenvalues. So that gives you sort of this total decomposition theorem of the spectrum. Okay, so to actually apply this to expanding posets, you have to prove that they have an approximate eigendecomposition. This has sort of long been known, at least in some reasonable sense, for simplicial high-dimensional expanders, originally in the work of Dickstein, Dinner-Filmus, and Harsha, and formalized a little bit more in our previous work with Bofna. The arguments are basically the same. They generalize pretty easily to expanding posets. Actually, the more interesting part is to compute this approximate eigenvalue, to show that the approximate eigenvalue, how it actually scales and is controlled by the regularity of the underlying poset. Now, I don't have that much time to go into this. I'll give sort of a light proof sketch of this. Basically, the idea is to reduce to some sort of combinatorial calculations. And so the first thing that we do is we show that any I-link, and in this case, this is the I-link of tau, where tau is sort of a rank I function. It's just all rank K elements that are greater than tau. And we want to prove that this function lies mostly within the ith eigenstrip. I think this is sort of intuitively true. I'm not going to go through how you prove this. Technically, it's a little bit annoying, but intuitively, it should seem reasonable. It's sort of these functions coming from level I. That the indicator of something at sort of the lifted indicator at something at level I should be in the ith eigenstrip. This is indeed true. And then we'll just make sort of a direct combinatorial argument. We'll argue that, okay, if this function is mostly in the ith eigenstrip, then its Rayleigh quotient with the walk in question is about the eigenvalue. And then we can just make a direct combinatorial argument about this Rayleigh quotient to prove that it's exactly this regularity parameter, that it's Rki over Rk plus 1i. I'll mention that this is actually not immediately so obvious. On a simplicial complex, this would be very, very obvious. But to get this to work on posets, you actually need middle regularity. As far as we know, you basically need that sort of the order structure is appropriately spread out to get that the regularity acts appropriately when you sort of walk between levels. It's a little bit technically annoying, but you can show, as long as you have this middle regularity condition, that everything sort of works out as you would expect, and you get this this regularity parameter. Okay, in the last couple of minutes, I want to talk about sort of applications of this spectral behavior to understanding combinatorial structure, in particular, the structure of something called non-expanding sets that was so crucial for proving the 2-to-2 games conjecture. So very briefly, what is edge expansion? Edge expansion is a combinatorial property of graphs that basically measures, given a subset of vertices, how many edges are leaving that subset, are expanding outwards. Something has good expansion if sort of many edges expand out of it. And it turns out that sort of characterizing what sets have very good expansion in graphs is a key tool in hardness of approximation. This is one way to think about a famous result called the KKL theorem. This is like such a characterization of non-expanding sets on the hypercube. And the proof of the 2-to-2 games conjecture basically relies on a type of characterization on the Grossman graphs that we mentioned before. These are some higher order random walk on the vector space analog of simplicial complexes. I'll define them exactly in a minute. And sort of the issue is that these characterization theorems are typically very hard to prove. They often go through like hypercontractivity and things that are sort of classically difficult. And sort of the more concrete motivation of this work is to try to work towards a more unified understanding of this type of characterization through the language of high-dimensional expansion and expanding posets. Okay, so what can we say? Well, formally, we prove the following characterization theorem. We say that if X is some very strong gamma high-dimensional expander, a gamma expanding poset, then the following two conditions hold. The first is that links, I-links give some type of canonical example of a poorly expanding set, in particular because they're sort of in the eigenstrip. The expansion of a link at level I is about 1 minus lambda I. And moreover, sort of some sort of converse holds. Any set with poor expansion is explained in some sense by its behavior on links. So if the expansion of your set is worse than 1 minus lambda I plus 1, that has to mean that you have sort of high variance across I links, that you can't look sort of random across elements at level I. Now, this theorem is actually tight. We give an exactly tight version of this for a couple special cases, like simplicial complexes and the Grossman poset, but it has sort of some major caveats. In particular, I haven't written it out here. We'll see it on the next slide, but these bounds are actually dependent on dimension, necessarily in this case, which means that if you consider families of complexes that sort of go to infinite dimension, the bound becomes essentially trivial, not strong enough to use. And this is also the regime that's sort of important for the 2-to-2 games conjecture. That's important for hardness of approximation. Now, this is known to be fixable in certain settings by considering infinity norm instead of variance. This is how the 2-to-2 games conjecture was proved on the Grossman poset. This was proved recently for simplicial high-dimensional expanders in work with Bothna, and also independently by Gur, Lifshitz, and Liu. But we sort of don't know how to do this on general expanding posets, or really on almost any object beyond simplicial cases and the Grossman poset. So maybe one more minute, let me give sort of a more concrete instantiation of this theorem, in particular on the Grossman, which is sort of our main focus. So let me remind you more formally, what are the Grossman graphs? So these are the graphs that have a vertex set given by, say, d-dimensional subspaces of fq to the n. And W and W prime have an edge if the dimension of their intersection is d minus 1. They're sort of as close as possible. Now, the first thing to notice is that up to laziness, this is exactly this up-down walk on the Grossman poset, right? You start at a subspace, you add one vector, you remove one vector. This will exactly give you something that is has intersection dimension d minus 1. The Grossman poset is just sort of the poset of vector space, subspaces of fq to the n ranked by inclusion. And a Q, we call a QE poset, is basically just a high-dimensional expanding subset of the Grossman. And our theorem basically implies the following characterization of expansion on the Grossman, on these sort of up-down walks on QE posets, on sort of sparsifications of the Grossman graphs. We prove that I-links have expansion almost exactly 1 minus q to the negative I, just like the Grossman. And moreover, any set that has an expansion much worse than 1 minus q to the negative I plus 1 has to have high variance across links, where high variance here means that if you're worse than this by delta, your variance must be at least delta over k choose I q. So notice that when k is fixed, this gives you a nice characterization, but when k goes to infinity, this is maybe not so helpful, right? It's telling you as k goes to infinity that the variance is like a little bit more than 0 in some little o of 1 way. Okay, so maybe I'll end with just a couple open problems. The first is sort of obvious. It's fixing this dimension dependence. Like I mentioned, this is sort of, it's known how to fix this for the Grossman poset, for simplicial complexes. In particular, for the Grossman, I should mention that you actually have to move to a different notion of locality. Links actually aren't quite the right thing to look at. So as we try to move forward and understand how to prove this type of dimension-independent characterization across generally posets, one of the interesting questions is sort of how to understand what is the right notion of locality to look at. How do we understand sort of what is the canonical example of a non-expanding set? When is it a link? When is it sort of a zoom in, zoom out, which is what it is on the Grossman? And the second thing I want to just quickly bring up is sort of proving this type of theorem under weaker expansion requirements. In particular, the sort of quantitative expansion that we require for our bounds is very, very strong. Certainly there are families that satisfy this, even sparse families. But many objects of interest are sort of quantitatively weaker high-dimensional expanders. And at the moment, sort of because our techniques have a lot of buildup and sort of error in the spectral term, we don't know how to prove really anything for quantitatively weaker expanding posets. And we also require sort of this strong two-sided notion of high-dimensional expansion, where your underlying link should have good sort of second eigenvalue and final eigenvalue. And I think there's sort of a broad opinion within the high-dimensional expansion community that really you should only need one-sided expansion to prove this type of thing. And it would be very interesting to sort of figure out how to get past this technical barrier the final eigenvalue of not needing this sort of last eigenvalue to be good. Okay, I think I'm out of time. Thanks so much for sticking around.